Hi everyone, welcome to today's webinar, Time Transfer and Synchronization, New Applications and Techniques. This webinar is brought to you by GPS World Magazine and our sponsor, EndRun Technologies. I'm Joelle Harms from North Coast Media, Senior Digital Editor for GPS World Magazine, and I'll be your event manager. Before we get started, I want to let you know that today's webinar will be recorded. You are currently in a listen-only mode. A recording of this webinar will be posted to gpsworld.com/webinars, and it also will be emailed to you tomorrow. At this time, I'd like to acquaint you with the ways you can participate in today's presentation. Please notice the Submit button in the lower left-hand corner of your console. Just type in the text box at the bottom left and click Submit to place your question in queue. We encourage you to ask questions throughout the presentation, although we will have a Q&A session at the end of the webinar. Our Twitter feed is also placed on your console. You can use the hashtag GPSWorldWebinar to submit any questions during today's webinar or to enter into discussions with other attendees. You may learn more about our speakers by viewing their photo and bio, which is in the upper left-hand corner of your console. If you're logged into your social media accounts, you can share the webinar's title, description, and URL with any friends or colleagues, all within the Share This widget, which is on the left-hand side of your screen. If you aren't already a GPS World Magazine subscriber, we'd like to invite you to sign up today for free. All you have to do is click on the GPS logo at the bottom of your screen in the dock and fill out a short form. Finally, if you experience any technical difficulties during today's event, select Help to submit your issue, and assistant producer Kelly Limpert or I will personally assist you. Now I'd like to turn today's event over to our moderator and publisher of GPS World and Geospatial Solutions, Alan Cameron.
Thank you, Joelle, and welcome everyone to Time Transfer and Synchronization, New Applications and Techniques. Today's webinar is brought to you by EndRun Technologies, a specialist in timing, and you'll hear more from EndRun during the course of the webinar, as well as 3 other speakers. We have 4 speakers coming at this topic from various angles today. Because the topic is a vast one and a very complex one, and it is not at all, although it's hidden from many of us during the course of our lives, it is vital to the conduct of our lives. Timing is not trivial. It is essential to the functioning of today's economy, and more precise timing and more precise time transfer and more precise synchronization are definitely to be desired or definitely required as we go forward. One of the many reasons for this is the increasing, I should say booming or perhaps even deafening demand for bandwidth as the internet and cell phones and all kinds of data-rich applications are passed over the internet. The need for bandwidth is just growing at an exponential rate. And, of course, bandwidth is finite. The key to using bandwidth more efficiently is synchronization and time transfer. And I'm going to let our experts on the panel today go into that in more detail. As I said, we have 4 experts coming at the subject from various angles. First of all, we'll have Ed Powers from the U.S. Naval Observatory, the mother of all time, in the United States at least. He'll tell us how the Naval Observatory sort of governs and administers timing in the United States. Then we'll hear from Ron Holm from EndRun Technologies. He'll talk specifically about timing in satellite communications, which of course is vital. Grace Gow from the University of Illinois will discuss timing and its role in the electrical power grid, which of course is essential to everything we do. And Richard Foster from Microsemi will discuss timing applications in defense, aerospace, and other industrial areas. We'll have a question and answer period at the end of our webinar, so I invite you to stay tuned, and as Joelle outlined, you can submit your questions through the webinar interface. I'll turn the electronic podium over now to Ed Powers, the GNSS and Network Time Transfer Operations Division Chief at the U.S. Naval Observatory. Ed, take it away.
Thank you, Alan. Yes, my name's Ed Powers from the U.S. Naval Observatory, located here in Washington, D.C., and I'm going to talk briefly, like Alan suggested, about our role in the timekeeping for the world and for the United States, and specifically deeply in our role in how we support the global positioning system. So we'll start off with describing a little bit about GPS and its time delivery service. So like was already alluded to, time dissemination is not what normally people think about with the global positioning system. They think about it as a positioning system, but because of the way it works, it is by its very nature, it's an ideal way of disseminating very precise time. And the use of the GPS as a time dissemination source has grown exponentially over the last 30 years. It supports many of our critical infrastructure, including the timing industry, the telecommunication industry, banking and finance, the power industry, and of course scientific users throughout the world. USNO has provided the underlying reference to universal coordinated time for GPS for over 30 years. U.S. public law, the Americas Competes Act, designates universal coordinated time as the time reference for all use in commerce. And the Department of Commerce, Secretary of Commerce, and the Secretary of the Navy are charged with coordinating precise time for the United States. And then USNO has been designated as the Department of the Navy to be the representative and providers of precise time for the Department of Defense and for the U.S. government. And our sister agency, the National Institute of Technology in Boulder, Colorado, is also been designated by the Department of Commerce to represent the United States on these issues and to maintain standards of time for the United States. And further, within the Department of Defense, like I mentioned earlier, the Secretary of the Navy directs the U.S. Naval Observatory to maintain these reference standards for Department of Defense activities. And because GPS is controlled and managed by the Department of Defense, funded by the Department of Defense, USNO provides the underlying reference for legal traceability to UTC for GPS. Now, how does GPS work? GPS timekeeping started in January 1980, and that's GPS time itself is considered the internal navigation time scale within GPS that's used for the navigation functions. GPS time itself rolls over back to zero every 19.7 years, and GPS is presently in its second time epoch. There's additional parameters broadcast in the GPS navigation message that allows you to convert GPS time to UTC and provide the fine UTC corrections that are used to synchronize back to USNO master clock. The internal navigation timescale within GPS does not account for leap seconds. It's a continuous timescale, and the leap second information is contained within the GPS message as an additional parameter for correction. So we break GPS timekeeping function into two broad areas: the navigation, the internal timing within GPS, GPS time, and then the UTC timekeeping, which is the timekeeping service that's provided to the world as the synchronization reference for timing activities. USNO keeps GPS synchronized back to UTC as maintained by USNO through maintaining a bank of specialized timing receivers here in Washington and our alternate master clock facility. These are perfectly calibrated, as perfectly as we can make them, calibrated receivers. We make these measurements, we provide them back to TUSOPS, who manages the GPS constellation daily. We have an interface control document that we maintain and provide this information to GPS. They then take our data, format it, and upload it to the satellites that broadcast it back to the users. This picture kind of shows the process. We measure the satellite signal, as you see across the top of the page, relative to UTC USNO, provide that timing information back to the GPS master control station that uploads to the satellites, and then we do the same function at our alternate master control facility as our backup. And the accuracy is specified in GPS today. There's both the PPS and SPS performance standards. They both basically reflect similar numbers, that the specification should be within 40 nanoseconds, 95% the error in the broadcast correction to the message. But in reality, the real performance, we've been able to maintain GPS synchronized UTC USNO within 2 nanoseconds, have averaged over a day for most of the past 15 years, and much less than a nanosecond since November 2010. This graph shows you the long-term historical measurements that we have here at USNO of the GPS timekeeping dissemination performance. The red line in the curve shows the UTC corrected data, and the GPS time itself is shown in the green curve. And you can see this is a daily average data. So this is what a user could expect if they could actually average the GPS signal over a whole day. This slide shows how USNO keeps the USNO master clock. It's not one clock, it's an ensemble of mini clocks. Presently about 75 cesium beam standards, 26 maser clocks, hydrogen maser clocks, and 4 of our new rubidium fountain clocks. They're all intercompared and averaged to create a super master clock. That's our reference for GPS and for our other master clock distribution techniques. And how does USNO perform relative to the other major laboratories around the world that also keep time for their countries? The green line at the very bottom of the scale, this graph shows you data going back to the 1990s. It's basically the last 20 years worth of data. And it's a logarithmic scale. And it shows you that we are presently, in 2015, we're something in the order of 2 nanoseconds in our ability to be able to reproduce the international standards for time. As I started off the slides, but the UTC timing information provided by GPS supports much of the critical infrastructure. So in conclusion, GPS provides the world basically the coordinating timing reference used for many activities, the telecommunication, power grid, banking, scientific. And USNO has been providing the underlying UTC reference now since the late 1970s, early 1980 time frame, and operationally was part of GPS for over 20 years. Well, that concludes my part of the presentation. I'll turn this back over to Alan.
All right, thank you, Ed. We will next hear from Ron Holm, the marketing manager at EndRun Technologies, and Ron's going to talk primarily about satellite communications, but also other aspects of timing. Ron, go ahead.
Thank you, Alan. I'm the marketing manager at EndRun. We're based here in Santa Rosa, California. We've been producing precision time and frequency solutions since 1998. The presentation here will be on satellite communications, and as Alan referred to earlier, the bandwidth drive for broadband Internet of Things certainly impacts the SATCOM industry. And GPS time and frequency standards within Earth stations are an important role of enabling the next generation technologies. So we're going to go through a little overview of SATCOM and how GPS time and frequency standards help with that in that industry. So if we take a look at SATCOM, basically we have the satellites in space. They're out there about 20,000 miles, and we have a number of Earth stations down on the ground that bridge the communications to the terrestrial network. Now, the region that we're operating in the RF spectrum is the microwave region. And in the chart, I'm showing some of the frequency bands. There's a few others, but these are some of the major ones. They run from 4 gigahertz up to 4 gigahertz, the C band up through the Ka band. And users, operators, they're assigned a slice of that spectrum that they must operate within. And so they need to utilize that spectrum as well as they can. As Ellen said, there's not unlimited bandwidth, and there's special challenges within SATCOM to find ways of providing higher data rates to customers. So if we take a look at the lower bands, they're very congested today. They've been populated. They're friendlier to work in. And the last few years, we've been pushing up into the Ka band region. Now, what makes it attractive, if you take a look in the column to the right, is the amount of bandwidth that's available on the Ka band. It's 13.5 gigahertz, which is a little bit, almost as much as the other 3 bands that I highlight there combined. And there's special challenges there as these higher frequencies come through the atmosphere and are attenuated through the atmosphere. And having a stable frequency reference at the root of these systems and keeping the noise to a minimum is key to providing these higher data rates. So this chart shows a block diagram of a typical Earth station. We take a look, we have the data on the left, the data coming in off the terrestrial network, and then on the far right, the uplink transmitters to the satellites, and then of course the receiving of the satellite signal. So we take a look at the top row, we have the modulators, which encode the data. And then we have the up converters, which drive and multiply that frequency up to the gigahertz range, into the microwave range. High-powered amplifier that shoots it up to the satellite, sends it out there. It's received about 20,000 miles out. And the satellites, which leverage that frequency, the accuracy and stability of that uplink signal, will down convert it and then send it back down to a receiving Earth station. Now, when it comes back down, it's a very low-level signal, and it needs to be amplified and work its way down to be down converted down to a demodulator and back out to close that communication loop. And with these devices, the modulators and the up and down converters, they all have independent oscillators within them. And if they're left standalone, they're subject to environmental instabilities, aging, and drift. And it's important that they stay very accurate in frequency and stability to make this whole system work. Managing these oscillators is difficult, so the solution is to put a GPS time and frequency standard into the base of these systems, distribute a reference frequency such as 10 megahertz out to the devices, and so that they can lock their oscillators to that reference signal. And GPS is, as you saw in Ed's presentation, is a very stable, highly accurate reference for these devices to synchronize to. So the satellite communication channels, as I mentioned, you get a slice of that spectrum. You might be operating at 18 gigahertz, but you may have only 40 megahertz to operate within. There's some guard band around that frequency because you have adjacent signals operators on an adjacent channel. So it's very important you stay within your slice, and it's getting sliced thinner and thinner to allow more operators onto that particular space. So if your frequency gets out of control and it's not accurate, you can interfere and walk over another signal and, of course, lose your own communications. And that makes you a very unfriendly neighbor. And the International Telecommunications Union and worldwide, and the FCC in the United States, who assign these spectrums, they'll be very upset if you do that, and it's something you want to ensure that you don't do. So a GPS time and frequency standard gives you that accurate base to reference. The GPS time and frequency standard, Ed went through the system, obviously rooted at USNO. The frequency, there's multiple atomic oscillators in the satellites. They're accurate to a parts in 10 to the 14th, extremely accurate frequency references. Ed talked about the timing, that's also there. So GPS time and frequency standards, they transfer this very precise time and frequency down into an instrument that's in the heart of the Earth station to provide that solid reference. Now, in terrestrial telecommunications networks, they qualify and have a standard for frequency, which is called Stratum 1. And for Stratum 1, all the devices need to operate within a part 10 to the 11th, which is rooted in a cesium atomic frequency reference. Well, with a high-quality GPS time and frequency standard, you're able to provide frequency that's part in 10 to the 13th, which is 2 orders of magnitude beyond what the Stratum 1 reference is. So an extraordinary solid reference. Now, one of the key noise elements that must be controlled in the SATCOM industry is phase noise. This has to do with the spectral purity of the oscillators within the devices, and it must be designed in from the start and carefully chosen, devices carefully chosen with the appropriate oscillators, because you cannot filter out this particular noise element. And with SATCOM, you need to have the strongest signal-to-noise ratios possible in order for some of the modulation schemes that I'll talk about in another slide to work. And it's cumulative within the system, and so oven-controlled crystal oscillators have the best phase noise, and they're specialized OCXOs that you should look at choosing. Because when you look at the root of the frequency reference, as they go through the multipliers, that noise gets amplified along with the signal by a factor of 20 log n, where n is the multiplication factor. Next slide, I show an output of a time and frequency standard with an ultra-low noise frequency reference. You'll see on the bottom, the horizontal, the offset from the carrier frequency or the reference frequency, which in this case is 10 megahertz. And then you take a look at the power levels per dBc per hertz on the vertical. The lower you are on that bar, the better. And if you take a look at the 1 hertz and the 10 hertz offset, you fall below minus 110 dBc, which is exceptional for a time and frequency standard. And that's what you look for as you choose an oscillator within your time and frequency standards. The next slide we're looking at here is the complex digital modulation. SATCOM, you're constrained, you cannot change your bandwidth. On terrestrial networks, local area networks, you can move from a gigabit transport to 10 gig or 100 gig. The operators must remain within this particular space. They look at different modulation schemes that are very complex. Phase shift keying is a popular one. This particular chart shows what we call 8 phase shift keying, and you take a look at it's encoded with small phase shifts, and as you start getting into more advanced schemes, the phase shifts become much smaller. And that means that in order to decode it, simple enough to encode maybe, but to decode it after it's coming back down, you must have strong signal-to-noise ratios, and that's where you need the low phase noise. Just a quick bit on large Earth stations, you need to have redundancy, and you need to have redundancy in the GPS time and frequency standard. On this slide, we show dual references feeding a distribution device. In this case, the distribution device monitors its inputs, and makes sure that the time and frequency standard is healthy and drives that signal within the Earth station. As you may have suspected, EndRun technology does provide time and frequency, GPS-based time and frequency standards. This is our Meridian 2, second generation device released in August of this year. It's a modular, customer configurable. A lot of design went into this for Earth station applications. Therefore, you have very low phase noise output capability, excellent short-term stability with a very low noise floor, highly accurate, as you see, the part 10 to the 13th per day, and stable. And also it provides timing services, which is an advantage of time and frequency standards within the substation. It's a network-centric device. It can push time out with the network time protocol or the precision time protocol to support Earth station operations, antenna control units, and what have you. This device shows a frequency distribution chassis. It's a dual input, 10 output, automatically switches between the inputs. A key element here is that it has extremely low additive phase noise. It also monitors all the inputs and the outputs and has alarm capability to Earth station personnel. A lot of redundancy on the supplies, high MTBF of greater than 20 years, and actually closer to 25 years. So obviously, as you saw earlier, you want a very highly stable device. So in kind of summary, GPS is an optimal solution. It's in the heart of the Earth station. It's a key enabler of these next generation modulation techniques and key to providing the highest data rates over existing spectrum. And it's hidden in the infrastructure. It's doing its job. It keeps everything in line. But it's really a beautiful optimal use of GPS. And so in closing, there is additional information on an EndRun website, a couple application notes on GPS frequency references for SATCOM, additional product info, and my contact information is there. I'd love to hear from you if you have anything additional. So I'll throw it back to Alan, and thank you very much.
Thanks very much, Ron. I want to pause for just a moment. We're at the midway point of our webinar. Before we resume with Grace Gow, I want to remind everyone in the audience you can submit questions via your webinar interface. I'm seeing a lot of questions coming in, and they're falling under three main groups. So besides a few particular concerns, I'll just give you a preview. Toward the end of the hour, we'll have some questions. I'll pose them to our panelists, and they're grouping largely so far under the changes in timing that may be upcoming with different satellite systems besides GPS providing a timing reference. Obviously, we're talking about Galileo, GLONASS, and Beidou. The vulnerability of timing to jamming and spoofing, obviously a topic of concern whenever GPS comes up. And third, applications of timing in various transportation modes, aviation, UAVs, driverless cars, and so on. Those will be some of the topics we'll visit in the concluding part of the webinar. For right now, I'm going to turn the podium over to Grace Gow, a professor at the University of Illinois, who's going to tell us about timing at the heart of the electrical grid. Grace?
Hi, thanks, Alan, for this opportunity. I'm Grace Gow, a professor at University of Illinois at Urbana-Champaign. And then today I will talk about our research focus on GPS-based timing with the applications for the electrical power grid. So for those of you who are not familiar with the phasor measurement units, or the PMUs, the PMUs are high-frequency, high-fidelity synchronized measurement devices that measures electrical quantities such as magnitude and phase of voltages and currents at many nodes over the entire power grid, as shown in the map of the United States on the upper right. In the time series plot of the voltage down below, PMUs provide measurements of much higher quality as compared to the traditional system called SCADA. The plot on the bottom right shows the power disturbance occurring in 2011. As we can see, the PMU measurements in the red curves, they're very dense and more accurate and timely, showing the voltage oscillations and the true start of the event. As such, PMUs have a huge potential in improving the control and post-event analysis of the power distribution network. For PMU synchronization, GPS-based timing is a strong candidate. I guess for all of us, we should all know that GPS is free to everyone. The GPS civil signals are readily available to all the users. And plus, GPS is a global service provider. That means it can cover a very wide global area. And what's more, GPS provides very precise timing. In fact, the timing and synchronization accuracy provided by GPS is below 100 nanoseconds. And this is way better than the required accuracy by the PMUs. However, GPS, because GPS is the received GPS signals are very weak, and then also the GPS signal structures are completely open to the public in terms of its civil signals. GPS also has some risks in terms of applying that for the power systems, such as it's vulnerable to jamming or spoofing events. The spoofing includes either the meaconing attacks, which is also a record and reply attack, or the data level spoofing. And what's more, GPS, even not under attacks, and GPS receivers can suffer from all kinds of noise or multipass errors or other receiver errors. As such, the goal of our research is to create and realize an algorithm that is robust against interference, have some level of spoofing detection while providing accurate and precise time. By addressing the risks, we are also addressing the similar issues of noise, multipass, and receiver errors, thus realizing an improved algorithm even when not under attack. So how to achieve that? Our approach is the multi-receiver position information aided vector tracking. Here on this slide, I show the architecture or the concept of our approach. Traditional way of using GPS for timing, we use one GPS receiver. Here for our approach, instead of using one single GPS receiver, we use multiple. Here I illustrate 4 GPS antennas and with 4 GPS receivers. We let all these 4 GPS receivers work together, and they are all driven by the same external clock. And then, so our goal here is to do the vector tracking for all the 4 GPS receivers at the same time. And then, because the GPS antennas are at static locations, we use the antenna position as the position information aiding for our big tracking loop of all the vector tracking of all the 4 GPS receivers. And then we solve for just the timing solution for the system. And then for this approach, our architecture, we can achieve improved redundancy and thus improved robustness. And then on this table, I'm just illustrating why we can achieve more robustness. From the left to right in this table, we show the comparison among scalar tracking, single receiver vector tracking or SRVT, single receiver position information aided vector tracking, and then all the way to the right is our approach of multi-receiver position information aided vector tracking, or the MR-PIAVT. And then for example, for just the scalar tracking, for each receiver, we need to track for N channels, and then where N is the number of visible satellites to the receivers. So for each channel, we need to solve for the 4 unknowns, which are the carrier phase, the code phase, the carrier frequency, and the code frequency. So given the same amount of information, we need to solve a lot of the unknown variables. And then if we look at the very right of the table, look at our multi-receiver position information aided vector tracking approach. We have a whole network of receivers. All the 4 receivers in the network, they work together. And then in terms of unknowns, we only need to solve for 2 unknowns, which are the receiver clock as well as the receiver clock drift. So from left to right, the search space is being reduced. Therefore, we can improve our redundancy and thus increase our robustness of the system. And then with this architecture and concept, let me then show you how to implement that. So I will show you the implementation architecture. So first, let's take a step back, and then this is, I guess you should be all familiar with this architecture for the scalar tracking. So I won't spend too much time on this slide. So in order to achieve our architecture, we first extend the scalar tracking to the vector tracking using just a single receiver but position information aided. Here on this slide, we show that in a single receiver position information aided vector tracking, the tracking effort is moved up from the channel level to the receiver level. In a single receiver vector tracking, instead of having to individually track the individual code and carrier of each channel, we only keep track of the position, velocity, clock bias, and clock drift of the receiver. We use the known true position and velocity as aiding information and have our Kalman filter only output the timing solution. And then from there, we further extend this architecture from the single receiver case to the multi-receiver case. In the multi-receiver position information aided vector tracking, we take the algorithm one step further. So similar to the single receiver case, instead of tracking each receiver individually, we track the reference clock bias and the reference clock drift of the multi-receiver network, where each receiver is triggered by the same stable external timing reference. So given this is the architecture, we also then implement that in our experiment. So here on this slide, I show the experimental setup, and then because we use we have this architectural multi-receiver structure, so we also have the test scenario of either 2 receivers or 4 receivers. And then in our experimental setup, we have GPS antennas, and then we also use the USRP as an analog to digital converter to digitize the signals. As for the external common clock, we use a chip-scale atomic clock from Microsemi. So I'm sure you will soon hear more from Rich Foster from Microsemi about their products. And finally, we also need a data link and then the power supply. And with that, I'm showing you the result. First, we showed improved timing accuracy in terms of clock bias. The left part is the result using the single receiver vector tracking, and then the right part is to use the multi-receiver structure. As we can see that the multi-receiver case has better accuracy, and then is smoother, and then it converges faster. And then the next slide, we show the timing accuracy in terms of the clock drift. Again, the multi-receiver case is on the right, and we can see it's a lot less noisy compared to the single receiver case on the left. So we mentioned at the beginning, like we want to make sure this architecture can provide the robust, secure GPS-based timing. So then we also simulated various timing attacks. First, we simulated the jamming. So for jamming, we purposely added noise at different levels and to simulate the jamming. We also simulated the mickening attack, which is also called a record and replay attack. For that, we would record the legitimate GPS signals at a different location at a different time, and then we add to our received signals from the antennas in our experimental setup. And then we combine them as our test signal. And finally, we also conducted experiment and a simulation for the data level spoofing. For the data level spoofing, this is a more clever way to spoof the signal. As we can see in this figure, so we just try to counterfeit the navigation message so that the received GPS ephemeris data in the navigation message are faked, and then they appear to be the satellites locations will be further away from the receiver. So if we do that by trilateration, if you calculate for the receiver navigation solution, so the pseudo ranges from all these virtually pushback satellites would still converge at the same location where the receiver is. However, the time will be off. So this is therefore this is a kind of a smart attack, and then it's harder for the receiver to realize there's such a spoofing attack. So I won't go through all the details of our experimental results. For more details, you can refer and go to read our papers listed here. And here I'm just showing you the summary of the experimental results of our multi-receiver position information-aided vector tracking. As you can see, we can successfully detect the meaning attack, the data level spoofing attack, as well as the receiver errors. And then it is also robust to noise, and then it can tolerate up to 15 dB of added noise for this architecture. I think that's all. And then in summary, I presented the GPS time transfer with the applications for the power systems. And then the algorithm here and then the architecture here can, of course, also apply to other applications that uses the GPS timing. And then we show that our multi-receiver approach can improve the timing accuracy, and then is also robust against various timing attacks, such as jamming, meaning, and data level spoofing. Okay, thank you.
Thank you, Grace. We'll hear next from Richard Foster from Microsemi Corporation, and following Richard, we'll have your questions. Rich?
Thanks very much, Alan. I'm going to talk about three things today. I'm going to just give a one-chart overview of Microsemi to familiarize you with the company. And then I'll talk about our Sync System 4388 product, and then some of the applications for that product. Microsemi is a global provider of semiconductor solutions for applications focused on delivering power, reliability, security, and performance. The company is headquartered in Southern California in Aliso Viejo. We focus on high-value, high barrier-to-entry markets, including communications, defense and security, aerospace and industrial. Company's revenue in 2014 was a little over $1 billion. We're at about 3,600 employees right now, and our symbol on the NASDAQ is MSCC if you want to look us up there. Okay, we launched a new product in September at the GNSS conference called the Sync System 4380A Master Timing Reference. It builds upon the SyncSource 4370A legacy product that we had. It was a reliable design that was vetted by the digital video broadcasting market. And it's a modular design platform that provides ability to add capability as your timing requirements change over time. So it delivers metrology-grade timing performance. It's a completely updated design that incorporates high-end components for excellent time and frequency accuracy. And it also includes a rubidium reference inside that and a timescale algorithm that deliver exceptional frequency stability. And finally, it has very low phase noise outputs for clean reference for use with measurement instruments. It serves a variety of high-end timing customers, including metrology labs and for calibration applications, aerospace and defense applications, and communications and satellite ground applications. We'll talk a little bit more about those toward the end of the presentation. Here's a quick look at the Sync System 4380A. This is the back side of the unit here. The key features, you can see it has 6 hot swappable expansion ports that support a broad range of input and output signals. It also has hot swappable power supplies. The hot swap feature is key in that it provides the ability to change things out for reconfiguration, so there's a lot of flexibility there, but also very important to some customers that have 24/7, 365 operations that can't have downtime. These things can be swapped out while the unit is still powered. You don't have to take the unit offline. In terms of our discriminating features, it's focused on performance. It's got a semi-codeless L1, L2 receiver that's included to mitigate the effects of ionosphere. It has a proprietary timescale algorithm that provides world-class performance. It also accepts a 10 meg input so that you can incorporate high performance atomic frequency references like cesium beam tubes and masers. And it also has auto survey feature that allows millimeter level antenna positioning, which translates into improved timing accuracy. And then lastly, it has compatibility with alternative time sources like two-way satellite time transfer, EndRun, and other sources of time that provide GPS independence. So let me move on to the next chart here. I'm going to talk a little bit more in detail about the benefits of the semi-codeless L1, L2 receiver. So if you look at the plot there on the chart, you can see that the red line is an L1 only GPS receiver, and that's its offset on the ordinate. There is the error in nanoseconds relative to UTC, USNO, and on the abscissa is days. And so this is about 10 days worth of data. The blue plot there is the dual band L1, L2 GPS receiver. And so you can see that at certain times during ionospheric events, you can get deviations in the timing accuracy for the L1 only receiver. And that's one of the issues that you're presented with if you don't have a L1, L2 receiver in there. So the Sync System 4380A incorporates this dual band receiver. The sporadic nature of these solar weather events causes timing systems to perform well on one day and poorly the next, unless you can compensate for those effects. And that's the benefit of the semi-codeless receiver. And that's what we use in the 4380. Another key feature of the 4380 is its ability to auto survey its position very accurately. So we have a mode where it goes into an auto survey mode and creates a RINEX file that you can upload to online processing utilities. You get back from that a very precise position with sub-centimeter accuracy, and that positioning is critical to achieving the timing accuracy specs on the system to get down below the 10 nanoseconds RMS that we provide with that product. Using GPS alone without the online processing can result in altitude errors. GPS is not as accurate in altitude, and in some cases that error can be up to 10 meters, which equates to roughly 30 nanoseconds of timing error. So most systems that spec that less than 10 nanoseconds RMS typically don't include the antenna position calibration. The precise antenna survey capability is critical for high-performance timing applications, as are envisioned for the 4380. On this slide, I'm showing the hot swappable modules that go into the 6 bays on the back. They're interchangeable and field replaceable. The unit automatically detects what modules you have loaded in there. Initially here we have an offering of 6 modules. The first one is a pulse output that covers PPS and DC iRig. It's got 4 ports. And then we have modules for 1, 5, 10 megahertz and amplitude modulated iRig as well. And then finally there's a time interval counter card that can be used that turns the box into a measurement instrument. So there are also other module types available. Specials are certainly possible for unique signal types. In terms of the phase noise performance, you can see on the right-hand side there for a 10 megahertz output module, it starts off at -110 dBc per hertz offset from the carrier by 1 hertz and goes down from there. Just briefly on the user interfaces, the unit has an Ethernet interface that provides access to a command line, and you can command the unit through port 1700. Also in the front there's a button that you can push that brings up and resets the IP address if you need to reset it. There's also a USB interface that you can use for the same kind of thing, and it also allows you to monitor external frequency references when you have our USB to serial converter. The Sync System 4380A is primarily a configure and install device. There's no front panel interface to enable inexperienced users to change the settings. We do have a graphical user interface, but it's not standard. You can contact us for details on that. Here are the specs on the unit. I think we've covered most of these already. The 10 nanoseconds RMS accuracy, the semi-codeless receiver. We do include a GPS antenna with the unit. That's standard. The frequency accuracy at 1 day is in 1 part in 10 to the 13. And then you can see the Allen deviation for different integration times there. In terms of applications and target customers, we're looking at high-performance applications, of course, for this kind of product, precision time tagging applications, precision frequency applications, certainly metrology and calibration applications. It can be used in scientific experiments. Companies will use it for R&D activities that build electronic devices that require precise time and frequency, and also for satellite communication systems, as Ron detailed earlier. In terms of customers, obviously national metrology labs, national R&D centers, the national flight test ranges, high-tech companies, both domestic and international, and universities and UARCs. So the focus for this product is on performance, as we've discussed. It provides part in 10 to the 12 frequency accuracy at any interval longer than 1 second. The other upper left quadrant there of the slide, you can see the stability plot. We talked earlier about the geodetic quality antenna survey that the unit provides automatically. In the lower left, shown as the benefits of the L1, L2 semi-codeless receiver. And then we didn't get into the details of it, but our timescale algorithm is inherently resilient to sparse GPS measurements. And with 5 minutes of GPS measurement 4 times a day, we can still hold into 6 nanoseconds RMS. And for defense, obviously radar systems require exceptional phase noise. There are applications there. Shipborne systems need to be synchronized for comm, radars, and control. Next generation systems like bistatic sensing systems require precise synchronization, and lower left, local area augmentation systems for precision landings, and of course synchronization for things like missile defense applications. And finally, for metrology and scientific applications, because time can be measured so accurately, it now forms the basis of 4 or 5 of the fundamental physical constants. So rather than a meter stick now, you can use a clock to define the meter and the speed of light. Satellite navigation systems need to be kept on time, and the unit can be used in those types of applications. And then large antenna distributed arrays around the world that have very long baselines, the product can be used for synchronization of those types of systems. So with that, I'll wrap it up. If you have questions, there's an email address here that you can send them to. And with that, Alan, over to you.
All right. Thank you very much, Rich. We're going to turn now to questions from the audience. And there have been a number of people asking about what happens when the new constellations come online. I'm just going to read a compendium of questions from different perspectives, different angles. They're largely the same, and then we'll have Ed Powers from USNO talk a little bit first, and then perhaps some of the other panelists. Here's what the audience is asking. What does the panel think are the steps necessary for the European Union to take to get Galileo accepted by the timing community? Somebody else wants us to discuss the implications of Galileo, GLONASS, Beidou, and QZSS on timing and time transfer. Can one rely on other satellites than GPS? What impact will the new GPS satellites and non-GPS GNSS constellations have on timing performance of GNSS receivers? And please comment on the differences between U.S.-developed GPS time and the timing systems developed by the other countries. Ed, let's go first to you.
Thank you, Alan. Let me first address GPS. GPS is going through a modernization effort, as most of you may be aware of, adding additional civil signals on the GPS L2 frequency and on the GPS L5 frequency. Those are going into operation over the next few years. There's many of the satellites are already broadcasting test signals. So that will add some enhancement for the GPS timing users by providing additional frequencies, better corrections for the ionosphere, and a little bit more robustness in case of local interference. Now, there are many other GNSS systems being built or there have been built around the world. Alan mentioned the list of most of them earlier. They're all working in a way very similar to GPS. For GLONASS, for example, they reference their timing signals ultimately back to one of their national metrology laboratories. And there's a big community of national metrology laboratories around the world that all provide time references for their own countries. And we all cooperate, the national time laboratories around the world, and try to maintain a unified time reference. And for the major countries, typically within 10 nanoseconds of each other. So for Galileo, they're going to reference several of their major timing laboratories as their fundamental timing reference. The Japanese with QZSS is doing the same thing with one of their national laboratories. USNO works with all these laboratories in helping create the world version of UTC. China's the same issue. They're all doing almost exactly the same thing as GPS, referencing their national metrology laboratories, providing a timing service just like GPS. Performance level, we'll see how well it works. They have to get their systems in operation, but one would expect them to work in a very similar way to GPS. Back to Alan.
All right. Thanks. Ron or Rich, do you have any comment on when or how user receivers or for example, the equipment that you all provide are going to incorporate, when or if they will incorporate time sources other than GPS?
I think, Alan, I would contribute. We kind of follow the as the systems mature and customer demand looks for solutions with alternate GNSS, you tend to see support flow into the products. So there are areas that we're carefully monitoring and so forth, and our devices are designed to evolve as those other GNSS systems come online. But that's kind of where we're at today, was focusing on GPS-based solutions with customized GPS time and frequency receivers. But that'll certainly evolve as these other systems mature.
Okay, we'll move on to a second set of questions. A number of people have inquired about timing in the transportation sector, specifically the autonomous transportation sector. We're about to enter a new era of involving autonomous transportation in the air and on the ground. Different people have asked, has anyone analyzed the time accuracy requirements for autonomous air vehicle, or UAV, cooperative collision avoidance? This person thinks that this will likely be driven by network communication synchronization rather than position accuracy. Someone else wants to know, how will timing be used to synchronize vehicle to vehicle or vehicle to infrastructure in the coming years? And finally, do you see any application for time synchronization in aviation? I'll throw that open to anyone on the panel to comment.
Maybe I can provide some comments. I think this is definitely a very, very good question. And then for me, this question mainly asks for the accuracy part of the GPS-based timing. But for me, I feel this should be similar to the power system case, that the GPS-provided accuracy is on the nanosecond level. That's actually very, very accurate. It should be more accurate than the required accuracy. But what I think I should care more is the security and then the robustness. So what if you use the GPS-based timing for synchronizing like the transportation, the self-driving cars, or like the UAVs? What if there's some malicious people trying to jam the GPS signal or trying to spoof the GPS signal and trying to mislead the GPS-based timing information? I think that would be a much higher risk comparing to the accuracy. Of course, accuracy is also very important for this.
Thanks, Grace. That leads into the third group of questions, and we have run slightly past the hour, but we'll continue for just a minute or two longer. Grace, you touched on this a little bit in your presentation, but several people are concerned about what alternative timing system is available when GPS is jammed, or how can you build a resilient time synchronization system under jamming or spoofing attack? Is timing and synchronization sensitive to spoofing? Well, yes, we've seen that it is. How is this being? How is this, or will this be addressed? Anyone on the panel care to comment?
Sure, this is Rich. I'll take that one, Al. As Grace pointed out, there are definitely concerns about GPS jamming and spoofing in this day and age. And so the ability to use alternative timing systems is critical, especially for the critical infrastructure. So along those lines, things like precise time transfer over fiber, two-way time transfer over satellite, and PTP over the networks are three ways that time could be transferred alternatively. If EllinoisRAN were to be implemented again in the United States, it is implemented in other parts of the world, that would be yet a fourth alternative source of timing.
Terrific. Well, I'm going to wind up our Q&A session and the webinar. I'd like to mention two things just briefly. One, Rich mentioned EllinoisRAN just now. EllinoisRAN tests are currently underway in the U.S. There's also experimentation and testing in Europe and in Korea. Actually, I just finished editing a news item about that will appear in the November issue of GPS World. Also, Grace mentioned just now nanosecond level timing, which has been kind of the gold standard up till now. But as I mentioned at the top of the webinar, better synchronization is going to be needed, and picoseconds may soon be the new standard. Ed Powers at the U.S. Naval Observatory has been in charge of some testing of some new techniques which can get to the picosecond level, and those are detailed actually in the October issue of GPS World Magazine, which is out now. That concludes our webinar on timing. I'd like to thank all of our presenters. I'd like to thank EndRun Technologies, the sponsor of the webinar, and I'd like to thank you, the audience, for attending. Come back with us next month on November 19th and December 17th, I believe, will be a two-part webinar on UAVs. UAVs design and operation will be the first part. UAVs in application will be the second part, specifically in mapping. Thanks to everyone, and back to you, Joelle.
Thanks, Alan, and thanks to our sponsor, EndRun Technologies, and all of our attendees. A recording of this webinar will be posted on the GPS World website and will be emailed to you tomorrow. To see those webinars that we have in the future for the last two of the year, visit gpsworld.com/webinars for more information. Thanks for attending.